So it seems like one thing that would be worth talking about, that I've made the mistake of talking about without introducing in some of the previous videos, is the idea of the kinematic quantities. And I expect you've probably been exposed to these before, but it's worth sort of highlighting them and particularly connecting them both to vectors and also sort of thinking qualitatively about them from a vector perspective. So there are three kinematic quantities that we deal with, and notationally in this class we'll tend to use the notation r vector for the position, v vector for the velocity, and a vector for the acceleration. From a definitional perspective, the position vector requires that you first define some coordinate system. So here's a three-dimensional Cartesian coordinate system. And if I've got some object that's located at some point in space, I define the position vector as the displacement vector between the origin and the location of that object. So it might have that object be some distance out in the x direction, some distance in the y direction, and finally some distance in the z direction. So you could sort of measure what the x, y, and z components of that position vector are. Now, in general, if things are moving around, the position vector is going to be some function of time, and the velocity is defined as the time derivative of that position vector. Finally, if the velocity is changing in time, the acceleration is defined as the time derivative of the velocity as a function of time. So in order to have an acceleration, you need a velocity that's changing. In order to have velocity, you need to have a position that's changing. Now, one of the things that I think is often the case is that people can kind of turn the crank with regard to position and velocity and so on, but often don't think very clearly about what they mean qualitatively, particularly what they mean qualitatively when you are dealing with a situation where things are moving in multiple dimensions. So let's just do a sort of couple of simple examples of that. One of these examples is basically on the module, but since I'm not very creative, I will do basically a replication of this. This is an example I think this comes out of Zimba's book, but he basically thinks about some fly, and the fly is flying around, and it follows some path as it flies around. And as it flies around, it does some things, like, for example, maybe it's moving slowly here. It continues to move at about the same speed here. Then it begins to speed up along this part of the path. It's still speeding up through here. And then finally begins to slow down. Right? So that's what the fly does. How do we think about that with regard to position, velocity, and acceleration? Well, at any given time, the fly is at some location. And so if we were to draw some coordinate system here, and say, okay, this is x, and this is y, at any given instant, the vector that goes from the origin to where the fly is located is the fly's position vector at that instant in time. The velocity tells you how fast that position vector is changing. And particularly what the change in the position vector is. If you think about it mathematically, right, the velocity, since it's the time derivative of the position, one way to think about that is it's a limit of the position at time t plus delta t. Oh, I put this in the wrong. Let me do this on another sheet of paper. So the velocity is the limit at time t as delta t goes to 0 of the position at time t plus delta t minus the position at time t divided by delta t, right? So qualitatively, what does that mean? Well, what that means is that if at some instant in time the object is located here, and at some instant a little bit later, the object is located here, right? This is r of t, this is r of t plus delta t. Then the velocity is this vector minus that vector. In other words, it's this vector divided by that time scale. So the velocity by delta t, and we take delta t to the limit of 0, so we get the derivative. So the velocity points in this direction that r is changing. Yeah. So let's come back to our fly then and think about that. And notice also that the more r is changing, the bigger the velocity is. So if I think about this point along the trajectory, the velocity is going to be pointing along the path, because at one instant in time, the position vector would be here. A little while later, since the fly is moving slowly, the position vector would be there. So the velocity points along the path. If I think about this point, the velocity should be pointing in this direction. And notice that since the fly is moving at the same speed here as here, the size of the vector is going to be the same, right? By the time we get to here, now the fly is starting to speed up, so maybe the velocity becomes bigger here and still bigger here. And by the time the fly is here, now the fly is moving in this direction. And if I think about what the change in the vector is, I've got this, say, this vector minus this vector, so the velocity is nominally down. And of course, since the fly is speeding up, the velocity vector is even bigger, right? Here, the velocity vector again will be big. And then finally, the fly begins to slow down. So by the time they're here, maybe the velocity vector looks like that. And the time the fly is there, the velocity vector looks like that. Okay. So the next thing that we would do is we'd think about, well, what is the acceleration, right? And in fact, if you think about what the definition of acceleration is, it's analogous to what the definition of velocity is with regard to position, right? It's the derivative of the velocity, or it's what the vector is that describes how the velocity is changing, right? So if we think about this point, right, the fly is moving slowly. A little while later, the velocity is the same, right? So this vector minus this vector is 0, and so the acceleration is 0 here. On the other hand, let's think about what's happening as the fly is going around the corner. When the fly is going around the corner, the velocity vector is changing, right? At this instant, it points this way. A little while later, it points this way. A little while later, it points this way. So if we think about sort of zooming in to just this location, sort of zoom into that, we would say at time t, the velocity vector points like this. At time t plus delta t, it points a little bit. The fly is turned a little bit to the right. So if I think about what the velocity at time t plus delta t looks like, this velocity at time t, this velocity at time t plus delta t, and boy, I should have used a smaller Sharpie, sorry about that. So my acceleration points inward, right? And notice that since the velocity is relatively small here, that change in the velocity is relatively small. So here my acceleration points inward, here my acceleration points inward, and so on, right? Along this line, the fly is beginning to speed up, and since the fly is beginning to speed up, the velocity is getting bigger. The acceleration is going to be basically this vector minus this vector divided by delta t, so the acceleration also points in that direction. And now we get to the more interesting part. As the fly is going around this curve, there are two things that are happening. One is the direction of the velocity is changing, and the other is that the size of the velocity is changing. So if I think about this vector and compare this vector to what it looks like a little while later it's going to be longer, and it's also going to be in a slightly different direction. And so my acceleration at this point actually has to be both forward to have the fly speeding up, and also inwardly directed to have the fly be making the turn. So at this point, maybe my acceleration vector looks like that. Now, a comment here is you can actually think about dot product, and here when you think about velocity and acceleration, what does it mean for the acceleration to be perpendicular to the velocity? In other words, if the acceleration dot with the velocity is 0, what does that mean? What that means is that the acceleration is not actually changing the size of the velocity, it's just changing the direction of the velocity. Whereas when the acceleration is parallel with the velocity, the acceleration is changing the velocity size, but not changing the velocity's direction. So perpendicular accelerations are going to change direction, they're going to cause turning. And parallel acceleration is going to yield either speeding up or slowing down, depending on whether the acceleration is pointing along the velocity or opposite the velocity.